Very well. Redox reactions in solution. As I mentioned in the previous video, this type of reactions are a little bit more intricate because it turns out to be the case that water is not an innocent player or a spectator player in the course of a redox reaction. In fact, water gets involved during the course of a redox reaction. And water has a few partners that need to be mentioned, specifically hydronium or H plus and hydroxide. These are the direct products of water auto-ionizing. And any of these three species, water, hydronium, and hydroxide, can actually play a role in the course of a redox reaction. So this makes the balancing of redox reactions a little bit more intricate. The actual rules are depicted here in the green box. We have to follow a set of steps. And the steps that we're going to be following are known as the direct method of balancing redox reactions. In the first step, we're going to balance anything and everything that it's not oxygen or hydrogen. Once that's done, we balance the total number of total electrons, and that will be the biggest step in this reaction, as you find out, or this process. After the electrons have been balanced, we then balance oxygens, not by the typical way, but rather by adding water to whichever side is lacking on oxygen content. And when that's done, we balance the number of hydrogens, not the typical way, but by adding enough H pluses to whichever side is lacking in hydrogen. So the process is a little bit different than what you've seen before. Let me show you an example so that we can exactly see how to balance the reaction via the direct method. And for reference, I will be showing you in a future video how to balance the same reaction via the half redox method, and you will get to choose which method clicks best with you. But right now, let's do it via the direct method. What this entails is that we are going to have to look at the individual charges of everything. But first, let's balance everything that's not oxygen or hydrogen. In this specific reaction, that would be chromium and vanadium. Those are the non-oxygen, non-hydrogen atoms. Notice that we have two chromiums on the left side, only one on the right side, so we need to multiply this one on the right by 2. Vanadiums are balanced on both sides of the equation. Alright, now we move on to the next part. This part is the most convoluted portion of the direct method. We have to now look at the individual charges of every element present in the equation. And to keep it simple, if you have an element by itself and no charge is written, the charge is understood to be 0. If you do have oxygen within a polyatomic ion, oxygen is understood to be 2 minus in charge. And then for the rest of the metals, we might need to do a calculation to figure out the charge, as you'll see in a second. But first things first, let me reassemble the polyatomic ions. So we know that dichromate has an overall charge of 2 minus. So I'm writing that outside the parentheses. And individually, each oxygen has a 2 minus charge. The same thing is true in vanadium. A +1 charge applies to the entire vanadium ion, but oxygen by itself has a 2 minus charge. Okay, now notice that for vanadium on the polyatomic ion and chromium in the polyatomic ion, I have X's and Y's because I don't know the charges yet, but I'm going to use the charges that we know to figure out the value of X and Y. And the way you do that is by setting up an algebraic equation. Basically what you do is you multiply 2 times X, 7 times minus 2, and you add them together. The idea being that the overall charges that come from the individual elements have to add up to the charge of the ion, in this case 2 minus. In the case of vanadium, 1 times Y plus 2 times minus 2 has to add up to plus 1, and that's what we're setting up here algebraically. All that needs to happen now is that we solve the equations. So minus 2 times 7 is the same thing as minus 14. Minus 2 times 2 is negative 4. Adding plus 4 to both sides, or plus 14 to both sides here on that equation yields a value of 5 for y. And upon solving for x on the left here, we end up finding out that x equals 6. This is how you find out the individual charges of the elements in the case where there could be more than one possibility for the charge. So let's input those charges for chromium and vanadium. Alright, now what we're going to do is look at the number of electrons. Going from chromium on the left side to the right side of the equations, we have a change of charge of 6 down to 3, and 6 minus 3 is plus 3 electrons for every chromium present. Likewise, for vanadium, we go from 0 to plus 5. 0 minus 5 is minus 5 electrons for every vanadium center. So now we know which one is the reduction, which one is the oxidation. The funny thing is that up until this point, we haven't even yet addressed step 2. It's really at this point that we finally get to balance the total number of electrons. But before we do that, we have to find out the charges. So as you can see, that's the more convoluted part of the direct method. Alright, now what we're going to do is balance the electrons. In some instances, the easiest thing will be to cross multiply the numbers. In other instances, you have to go with the lowest common denominator. But right here, there is no lowest common denominator, so we will just multiply, cross multiply each of them by the corresponding number. Oh, one more thing. Since we're dealing with fractions, we have to account for the amount of chromiums and vanadiums present in the equation. So we multiply the fraction by 2 chromiums, and we multiply the fraction out here by 1 vanadium to get rid of the fractions. Now that we have the electrons, now we do the cross multiplication I was telling you about. So we're going to multiply the top number by 5 and the bottom number by 6. But notice what has happened. The moment I multiply the top portion by 5, I also multiply the direct reactant and associated product by 5. The moment I multiply the bottom portion by 6, I multiply the direct reactant and direct product by 6 as well. This balances the number of electrons, but it also balances completely and properly the non-oxygen, non-hydrogen atoms. Now we're ready to look at the oxygens. If you look carefully, you'll find out that 5 times 7 gives us 35 oxygens on the left side. 6 times 2 yields 12 oxygens on the right side, meaning that we're missing 23 oxygens on the right side of the equation. So we literally add 23 waters to account for the discrepancy. Now, that also means that looking at the hydrogens, we have 46 hydrogens on the right side and no hydrogens on the left side. So we need to add 46 hydrogens, but they have to be specifically in the form of H+. They cannot be regular H with no charge, and it cannot be H2. It has to be H+. And at this point, you have balanced the reaction. One way to double check that this is done correctly is to look at the overall charges on both sides of the equation. We have a +1 charge for hydrogen, 46 of those, that's plus 46. -2 charge for dichromate, and 5 of those, so that's -10. And then here's a charge of 0, so no contribution. So we have 1 times 46 minus 2 times 5 plus 0 times 6, which added together is 36. On the right side of the equation, we have 3 plus times 10 plus 1 plus times 6, and then this is neutral, so no contribution. And 3 times 10 plus 1 times 6 is 36, meaning that the equation has been indeed balanced correctly. And this is how you balance the reaction via the direct method.